Hello children, welcome to Yamuna's physics classes. Today we have to discuss a simpler topic of refraction known as two different topics we are discussing today. One is real depth versus apparent depth. The other one is advanced sunrise and delayed sunset. Both are real life issues or real life concepts what we are coming across in our day-to-day life. So it's of practical importance rather than theoretical importance. Okay, so let us see what are they. First let us see what is real depth and apparent depth. For this you can think about an aquarium or a water tank or a fish tank, something like that. Let me show you a simpler version of it. So here we have a simpler version of an aquarium. This is the simplest version of an aquarium what you can have. So here you have a water, here you have some pebbles below. Okay, now when you watch it from vertically up, suppose I place my eyes vertically above the tank, just vertically above, the incident ray is going parallel to normal, gets reflected parallel back or retraces the path so that I and R goes to 0. At the time the object, the stone or the pebble is just underneath the water, I feel it the same. But for an oblique incidence, if I am placing my eyes a little bit slanting, not like this, just I look at in a slanting manner, it seems whether the pebble is a little bit raised or has it moved up from the real depth. So initially the depth is known as real depth. Now I feel like it's not original, but I feel like or apparently I visualize that the image is a little bit raised or the stone is somewhat raised. That is known as apparent depth. So this is what I meant, and we can come to the pictorial representation now. So that's what the evidence I have to show, and this is the pictorial representation of the discussion. So this is the water tank, water area. This is the pebble which I placed initially below the tank. It's below the tank. So the pebble is at a height HO or the object from the surface of the water level. So this is the surface of the water level, this is the position of the pebble, so this is the real depth. HO is known as real depth. And from this I am watching the light rays coming from the pebble to the atmosphere or air. So incident medium is the denser medium N1, first medium. Refracted medium is rarer medium N2, the second medium. So normal incidence, normal refraction. So here I equal to 0, R equal to 0. Clear? Just like a plane mirror. But look at the yellow ray. This is somewhat an oblique incidence. So this ray is going in this manner obliquely, falls at the point A, which is the point on the surface of separation. At the point A, you have a normal like the dotted line, and this is the angle of incidence I here. So light ray is going from denser medium to rarer medium. So you know it bends away from the normal. It is going from denser to rarer. So what happens? Velocity increases. Refractive index decreases. So it moves away from the normal. So this is angle of refraction R, angle of incidence I. Clear? Now we are going to find a beautiful relationship between N1, N2, HI, HO, the four parameters. Once again, N1, N2, HI, HO with a simple tool, Snell's law. Now when do you apply Snell's law? Where do you apply Snell's law? Where the refraction takes. Here in this figure, the refraction is taking place at the point A on the water surface. So for the point A, incident medium, refracted medium. So incident medium refractive index N1 sin I equal to refracted medium N2 sin R. Clear? Now in the whole ray optics we have certain assumptions, and the most important assumption is all angles are small. Whatever angles you come across in ray optics, you consider they are very, very small. For small angles, underline the word small angles, sin theta is theta, similarly tan theta is theta. So instead of sin I can substitute tan I if theta is small. That's a condition. So I use instead of sin I, tan I. Now from the figure, beautiful figure, you can see that if this is I, this is exactly I. Why? Z. Follow me. This is the Z shape. I and I known as alternate interior angles. Two parallel lines cut by a transversal. Angle I, angle I. Similarly, this R and this R, these two lines, the normal and the rate retraced, these two are opposite angles. So they are R. This is double arrow or the double stripes shows R. Here again the double stripes shows R. So here again you have an Z. Look at this Z. Start from here. This is Z. So this is again alternate interior angles. Two parallel lines cut by a transversal. These two are the same. So this I, this R. You have two triangles, right angle triangles. This is the right angle. This is the right angle for both. One triangle is like this, A, I and the point, A, O and the point. I have marked this distance as X. That's enough. Okay. So from this write tan I and tan R. What is tan I? Opposite by adjacent. X by HO. What is tan R? X by HI. This is HI. This is HO. So substitute. N1 tan I. What is tan I? Opposite by HO. N2 into tan R. What is tan R? X divided by HI. Here X cancel in the both sides. What you will get? N1 by N2. N1 divided by N2 equal to N12 equal to HO upon HI. What is the meaning of N1 and N2? Let's come back. What is N1? Refractive index of water or the incident medium. What is N2? Refracted medium. So we will say refractive index of N1 with respect to N2. Refractive index of 1 with respect to 2. Which is 1? Medium 1? Water. Which is medium 2? Air. So what is this answer going to be? You know the refractive index of water is 1.33. If you want, you can write the value. The value is 1.33. That's a value here, and this is the value 1. Refractive index is having a value 1. So what is this answer? 1.33 by 1 means 1.33. How did you get it? Very simple relation. Height of the object divided by height of the image means what? Real depth minus apparent depth. Suppose this is 4, this will be sure 3 by, because the ratio should be 1.33. Is it not? So height of the object means what? What is this? Is real depth is what? What is real depth? HO object. What is this? Apparent depth HI. So the ratio HO by HI, this is HO, this is HI. This ratio gives the relative density, relative refractive index or refractive index of water with respect to the second medium, that is air. So the answer is refractive index of water with respect to air is real depth divided by apparent depth. Beautiful relation to memorize. So how to find simply the refractive index of water? Divide apparent real depth divided by apparent depth. Hope it is clear. Okay. Now you have the second topic. What is advanced sunrise and delayed sunset? Advanced sunrise, delayed sunset. From the word itself it is clear. Advanced means what? Even before sunrise you can see the sun. What is delayed sunset? Even after sunset you can see the sun. That is known as delayed sunset. And one word answer is atmospheric refraction. That's a one word answer. Now to go to a little bit in detail, the figure shows everything, whatever you want, it is there. So here you have the earth. This is the atmosphere surrounding the earth, and I am standing somewhere on the surface of the earth known as sea level. Usually we will say sea level as the surface of the earth. Why? Fully covered with sea, a little bit of sand or mud, whatever it is. A little bit of land and mostly water body. So you are standing somewhere on the sea level. Seashore you are standing and looking to the sea, where you see the entire sea is feeling like it is just close and touching the sky. You see a portion, here all you have the sky, the other part you can see the sea. So a line, a straight line you can see where sea and sky is getting separated. That is known as horizon, or it is simply a tangent to the earth's surface. Wherever you stand, you put a tangent on that particular point. That is known as horizon. And rising and setting, sunrise and sunset, is visible to our eyes when sun crosses the horizon. But here what is going to happen is, sun is going to rise. Suppose sun is coming to rise up. It is coming and coming and coming and coming and coming, and even before it crosses horizon, I could see it. How? That's a question. Similarly, sun is set, already sun is set. Sun is gone down, not coming up, it is well inside the horizon, gone down the horizon. Even after that, I can see the sun. What's the reason? The reason is, we can see the sun only when it is at horizon, because before that the rays coming from the sun will enter the atmosphere, gets refracted. But the problem is, they are not reaching our eyes. The refracted rays not reaching our eyes, that happens only when it crosses the horizon. Till then the ray will be falling somewhere here, not to our eyes. But as it crosses the horizon, it comes to our eyes. But here it is advanced and delayed, means it is coming up and up and up and up, and it is coming a point very close to the horizon. It's not cross, just very close to horizon. At the time the rays are coming and entering the atmosphere. This is atmosphere. But you know, the highest speed for the light is in vacuum. That is 3 into 10 to the power 8 meter per second. The magic number, you know. But here the refractive index is purely 1 in vacuum. But as you enters the air or the atmosphere, the value of refractive index slightly increases. It goes to n equal to 1.00029, a little bit higher. So the ray gets slows down. A little bit it comes slower. Means light ray is coming from a rarer to denser. Comparatively, this is rarer, this is denser. That slowing down results in the bending of the ray. The refracted ray bends towards the normal by half a degree, just half a degree. But I have shown very magnified picture for the clarity. It is really very half degree bend. And this half degree bend just remains there for 2 minutes. Just 2 minutes. Half degree bend refers to nearly 2 minutes time. So just before sun, really sun is not here, 2 minutes before sunrise I can see the sun. Similarly, after the sunset, sun has gone down, even then I can see the sun for 2 minutes. That is due to atmospheric refraction. So what is horizon? Tangent to the earth's surface is called horizon. Then when light ray enters from vacuum to atmosphere, it is coming from vacuum to atmosphere. It slows down. I told you why it is slowing down. Due to the comparatively this is denser, this is rarer. Slows down and bends. Bends towards normal. Why? Rarer to denser. The rays reaching our eyes, that's an important factor here. We are not seeing this ray. This is the incoming ray, but our eyes are watching the refracted ray, that bend ray. It is retraced. We retrace that bend ray, and our eye and mind visualizes only the straight line path of light, not the bend portion. So our eye senses this ray. This is myself. I am standing. I could see. My eyes are watching not the sun, this sun. So the rays reaching the eyes are the bend rays retraced back. So the bend rays are produced back. So I feel the sun is here. Actually, sun is not up to the horizon. It is within the horizon. Even then I can visualize the sun. This deviation is just half a degree. And half a degree corresponds to nearly 2 minutes. So even before sunrise, 2 minutes before and after 2 minutes I can see the sun. This is again a very beautiful evidence to show that there is refraction, and it is known as atmospheric refraction. Hope it is clear. Thank you for listening.